Let's see if we can learn a few things about limits, and I'm not really going to delve too much into the sort of real analysis definition of a limit. We're going to look in terms of, single variable calculus. We're going to look at limits in that regard. So let's take a look. And I mean, there's various definitions of limits that you may hear in Calculus 1. However, the one that I prefer that's quite intuitive and also very kind of helpful graphically when you're given the graph of a function to determine certain limits is how a function behaves as x approaches a certain value. Now, this notion of approaches is, I mean, again, in a real analysis sense, there are various ways to define how a function or how a value approaches another value. However, the way I like to think about it, if you want to think graphically, then suppose you have some particular function over here. Let's assume it's a parabola, I don't know. Okay. It's, going to continue on to infinity. And suppose we pick some particular value over here. Let's call this, I don't know, x equals a. Then when we want to think about, what happens to x and how it kind of approaches a, then we can think of like maybe, let's suppose we have this point over here, which could be like, I don't know, a plus 1. And then we can think kind of what happens to the function as the distance between this particular value we picked over here and our value a starts getting closer and closer to 0. So maybe this is a plus, like, I don't know, 0.7 and then 0.5, and then just keeps getting closer and closer to a. And then we're going to look at what happens kind of to the function as a result of these changes in our x value as they start getting closer to a. We'll maybe converge to a particular value. Now, there are two kind of notations that we need to be very familiar with when it comes to limits. We have over here, this is what I like to call kind of, I mean, it doesn't really have much of a formal name, but I like to call it kind of the total limit, because it is just the entire function, how it behaves as x approaches a from both directions. And the notation over here, we have the limit of f of x as x approaches a. And then we have kind of two sort of subcategories, if you will. We have the limit of f of x as x approaches a from values greater than a, which is what this little positive sign or positive superscript denotes. And then as x approaches a from values less than a, which is what this negative, superscript denotes. And again, if you want to look at it graphically, we can come up over here to this example. And actually, let me pick another color. Let's take green, for example. Let me highlight this. If we want to think about it graphically, we can say, okay, from values that are greater than a, we're going to be kind of, as we said, we can just, take any value greater than a and then start seeing what happens as we start picking values that are closer and closer to a. And the definition of closeness, I mean, again, a lot of definitions of that, but the way that I like to think about it in terms of this context would be just kind of seeing what happens to the distance between these two values. So we just keep approaching a, taking kind of small, I guess you could say, step sizes towards a, and then we see what happens to the function as a result. And so here we'll have this particular point would be, a comma f of a, and then, that can kind of help us determine what the function is going to either converge to or just in general how it's going to behave as we approach a from values greater than a. We just look at this, what we call one-sided limit or single-sided limit. And then let me take this red color here. And then when it comes to values that are less than a, then we can kind of basically just do the exact same thing, but for values that are less than a. So we can take any arbitrary value that is less than a, for example, this one over here, and then we can see, kind of what happens as we start taking values that are closer and closer to a, but that are still less than a, and then we see kind of what happens to the function as a result. So we kind of see what the function does, what it, how it behaves. Does it converge to a particular value? Does it kind of diverge and asymptote towards infinity? We'll see different examples of that. So this is kind of just a general definition of a limit. So these are the one-sided limits, and then if we wanted to take, the overall or the total limit, then that would just be taking into account both of these, both the one-sided limit from the values that are less than a and the one-sided limit from the values that are greater than a. And if these are both equal to each other, so let's suppose that, I don't know, in this particular case, we'd have, the limit of f of x as x approaches a from values that are greater than a. In this case, I mean, just looking at it graphically, This is just a very arbitrary example. This is not always going to be the case, as we'll come to find. In this case, it's equal to the limit of f of x as x approaches a from values that are less than a. And we know that in this, again, this is all just an arbitrary particular example. We have this being equal to f of a. Now, this is not always going to hold true. But then in this particular case, we see that these two limits exist. They're both equal to some particular value, f of a. And we see that they're both equal to each other. And so because these are both equal to each other, we can say the limit exists. So we can say the limit, or the total limit I should specify, as x approaches a, this exists. And it's going to be equal to, let me just write it like that, this is going to be equal to f of a. Again, not always going to hold true, but as of right now, we can say, if we want to think about this sort of total limit, then we can just look at the single-sided limits, see if they both exist, see if they're both equal to the same value, and then that can help us sort of determine whether or not this total limit right over here exists. So let's go ahead and look at a few particular examples of this. So let's suppose that we're taking, we have f of x is equal to, I don't know, let's say maybe sine of x. And then we take the limit as x approaches perhaps pi of sine of x. And then we can look at this graphically if you want. And we know what, we all know what sine of x looks like. I mean, I'm not going to really draw it in too much detail. It's going to be this sort of uniform wave, and then it's going to continue downwards. That's not very nice, but nonetheless. And then let me actually select this this yellow color here. Let's say that this right over here is x equals pi over 2, and then this point right over here is going to be x equals pi. And we know, it's going to be the maximum value. And so essentially, when we're looking at this function, we see that if you want to take into consideration both the one-sided limits, or both of the one-sided limits, we can look at the limit of sine of x as x approaches pi from values that are less than pi. And I mean, we can look at it graphically if you want. We can see over here, we surpass pi over 2, and then we kind of keep decreasing downwards, and we converge to this particular value over here, which is, or this particular point, I should say, and that's going to be the point pi 0, which we know, just from our basic trigonometry. So we can say that this limit exists, and it's going to be equal to 0. And then what about the other one-sided limit? If we want to look at, the limit of sine of x as x approaches pi from values greater than pi. And again, same exercise, we can just kind of generally look at any values of pi, or any x values that are greater than pi, and then kind of see what happens as we start getting closer and approaching pi. And again, we're going to see we converge to this particular point over here, pi, 0. So we can say this limit's going to be equal to 0. So we've established that these two limits, they definitely exist, right? I mean, these are like valid limits. They can be equal to 0. So these both over here, these both exist. And another kind of interesting property that we should note is that these are both equal to each other. So both of the one-sided limits are equal to each other. So this is equal to this over here, the other one-sided limit. And we established that they're just going to be equal to essentially f of pi in this particular case, or sine of pi, I should have written. So they're both equal to each other, and they're both equal to the function evaluated at that particular point. And so then we can just say right away the total limit. So just as x approaches pi, we're going to neglect any superscript of sine of x. Is just going to be equal to 0, right? Because we established this is equal to 0. So that's one particular case that we may have. But let's kind of look at a case now where these two statements don't hold true. Maybe, these two aren't always going to be equal to each other, and we're going to see kind of what we would do in that case. So let me go ahead and graph out a particular function. I'm not really going to consider the equation of it. But let's suppose we have maybe a piecewise function. That looks quite odd. And then right over here, maybe it continues off. Actually, let's make it a linear function over here and the negative slope. All right, that suffices. And then let's continue, or let's consider this value over here. Let's say this is x equals -1, for example. And then over here we'll have this particular value. We can say maybe this is, I don't know, maybe this is equal to 1, and then this particular value maybe we can say is equal to like 2.5. Again, this isn't really drawn to scale. And then let's consider its limits right over here. So let's suppose this is the function f, and then we want to consider the limit of f of x as x approaches as x approaches -1. And we're just going to look at it in general, the total limit. So it's helpful to consider the single-sided limits. So let me do that in a different color. So first we can consider, let's look at maybe the limit from values that are less than -1. And then we can kind of graphically observe that. So we can see we have maybe this point over here would be like, I don't know, -2. And we have that particular value, and then we get closer and closer, maybe -1.5. And then we approach even closer, and then we seem to converge this particular point over here, which is equal to 1, as we wrote down. So we have a single-sided limit. I mean, this definitely exists. This is also a valid number, so it does exist, right? But then let's take a look at the other single-sided limit. Let's look at the limit of f of x as x approaches -1 from values greater than -1. So again, we can take maybe 0 over here, and then we kind of get closer and closer, maybe -0.5, and then eventually we approach -1. Now, the function itself evaluated at this point is going to be equal to 1, but when we're considering the single-sided limit from this particular direction over here, it doesn't seem to be equal to 1. It seems to be approaching this value over here, 2.5. Now, the function may not be equal to 2.5 when we evaluate it at -1, but maybe its limit's equal to 2.5. And so in this particular case, the limit is equal to 2.5. And this is also valid. I mean, if you want to look at it graphically, we can see like it doesn't necessarily approach 1. It actually approaches this value 2.5 over here. I did not mean to erase that. Let me fix it. So yeah, it approaches this value 2.5, even though the function evaluated at -1 is not equal to 2.5. So this also exists, right? But now we've kind of reached a little bit of a problem, because we have two existing limits. These are both, valid limits. They both exist, and we can determine them graphically quite easily. However, these aren't equal to each other. So let me put, these are not equal to each other. The single-sided limits aren't equal to each other. So then what does that mean in terms of our kind of total limit? Well, in one direction, our function is behaving a certain way. It's converging to 1. But then in another direction, it seems to be behaving in a different way. It's converging to 2.5. And so then we can say, okay, maybe the single-sided limit exists. However, this sort of total limit we can say does not exist. So that kind of gives you a general sense of what would happen. Does not exist. Sorry. So this kind of gives you a general sense of how we can kind of graphically determine limits and how to distinguish between the single-sided limits, the total limit, and the function evaluated at that point. And this actually is another crucial statement we should make, is that the limit of f of x as x approaches a, and it can be from any direction, we're just going to say in general a, this is not always going to be equal to the function evaluated at a. I mean, there are certain conditions for this to hold true, but I mean, right over here, we have a counterexample of that, right? We can see from this direction over here, it approached 1, while from this direction it approached 2.5, and the total limit didn't even exist. So these two both existed, but one of them was equal to the function evaluated at x equals -1, but the other one wasn't, but it was still the limit. So that's one kind of outcome we can get from this. And in general, another outcome we can get out of this is that if the limit as x approaches a from values less than a is equal to the limit of f of x as x approaches a from values greater than a, and we say that this is equal to, I don't know, maybe some value, we can call it capital L, and so this exists over here. If these two limits exist and they're equal to each other, then we can say that the limit as x approaches a, the total limit of f of x, is going to be equal to L. So these are some kind of important outcomes. We're gonna delve much deeper into limits, of course, throughout the, I guess you could say the course of these videos throughout this playlist. But this is just a very basic introduction to limits, single-sided limits, and kind of the existence of a total limit.